All right, thank you so much. Yeah, so the session today is back EMF measurements for electric vehicle motor production. Honestly, it could be any motor production, predominantly permanent magnet. So I hope you guys find this interesting, and I'll get started. So quick introduction. We're going to start off with back EMF and motor construction, kind of the fundamentals. Anybody who's sat through one of my presentations, I like to start with kind of the basics. We'll get into what a back EMF test looks like, kind of the nuts and bolts, the tactical, how do we actually implement a test for this? We'll go through a testing example. HBK has done quite a few of these tests in both the automotive and other industries. So we've actually built up a really nice book of examples, and this is one that we can share. We'll then look at some accelerated back EMF testing. How can we maybe do this test more quickly or do it with fewer resources? And then conclusion. So jumping in, end of line testing for electric powertrain. All right, so start with the real basics. What is production testing? So production testing requires, the requirements are different than R&D testing or lab testing. We really need a robust measurement in a production environment. We need to make sure that this measurement is going to work every time, and that we're going to be able to be up for 8, 12, 24 hours a day, making reliable measurements. We need to have decision making. It's not we take data and we interpret it for days. It's pass or fail. We need to have some quick metrics where we can decide if something was manufactured correctly or not. And we're doing thousands of these a day, so it needs to be fast. So we need to measure something. That metric needs to mean something to us. Getting farther down, maybe if we're having a lot of issues, we need to have some data. Not a lot of data, but a little bit of data. So we can start to do root cause analysis to understand if we're having production defects. This could be from warranty, this could be from elsewhere, but we're going to be using large data sets. We need to have communication with the production line. We need to tell an automation system that it was a pass or fail so it can make a decision on what to do with that part. And lastly, again, and this kind of comes back to the root cause analysis, we want a database of results and production statistics to see if our tooling is changing, to see if our suppliers' materials are changing, to understand what might be causing defects in a production line. One of the biggest issues we're having right now in automotive is the yield of production lines. We're throwing out so many parts. And good production testing, good validation of manufacturer, of our supplier goods can really help us increase those yields, have a better output, have a higher percentage of quality goods. So what can HBK do, or kind of what can we do in general with measurements for electric powertrain production? Well, on a battery, you can look at the power output of a pack. You can look at the thermal requirements of a pack. I'm not going to speak to that today. For an inverter, you can look at the efficiency. You can look at the power outputs during normal conditions. You can look at the power outputs during faults. Or you can provide feedback to something like a power HIL. So that's what you can do for the inverter. Again, not going to talk about the inverter today. For a gearbox or transmission, we can look at the efficiency. We can look at the power output. We can look at gear defects, noise and vibration. So these are things that we can measure to understand. We're not going to look at that today. We're going to focus in on the electric motor itself. And with the electric motor itself, you can measure a few things to understand if it passes or fails. You can look at the efficiency. This can tell us quite a bit about if the whole motor was constructed well. You can look at the power output. If I give an input and I'm making peak power, that can tell us a lot about how the machine was constructed. But we can run some individual tests to look at stator construction, rotor construction, magnet strength, and then noise and vibration to understand if this test was executed correctly. So we're going to zoom in on a couple of these points, the ones I have highlighted. All right, back EMF and KE are some terms we hear quite a bit. So let's do a little mathematical definition. So back EMF, or our little epsilon, equals negative the number of turns. So N is the number of turns of wire, so the number of coils, times the change in flux per change in time. So what's the derivative of the magnetic flux? So what this tells us is if we have a changing flux, basically if we have a moving magnet, we're going to generate a voltage. And this is what commonly gets referred to as back EMF. And it's really demonstrated by my kind of little illustration over here. I have a north magnet and a south magnet. And if I move that magnetic field, because our permanent magnets create a magnetic field, by a coil of wire, and that wire has n turns, the speed of which that magnet turns, the change in flux per time, times the number of turns is going to equal our voltage. So we're basically just getting a voltage by spinning a magnet by a coil. Ke, which is a machine constant, and we'll hear people talk about this all the time, is our back EMF, or our negative N d phi dt, over speed. So it's a ratio metric. How much voltage am I creating per the speed of the motor? So it's really what's my peak voltage per my no load speed is a simple way of cooking it out. Now I have some issues with this basic equation, but that's another discussion for another time. At the end of the day, it's what's our voltage per our speed. This will give us our machine constant. If anybody wants to talk about why I think V peak is not the greatest of metrics, I might get into that later if we have time. Otherwise, I'd love to have an offline discussion. But basically, our back EMF, our Ke, our machine constant, is if a magnet is moved by a coil, it will create a voltage proportionate to speed. So this is really the principle that we're working off of. Okay, let's look at our motor construction. What is our actual motor built of? What can we test? So here I have two images. I have a picture of a stator. This is a pretty simple stator, and we can see that we have some laminations pressed together. We have these steel laminations. We have N turns, so we have these copper windings, these bobbin wound windings, excuse me, with a number of turns. We have our solder connections here, and we have sensors that are inserted into the rotor for position, or excuse me, into the stator for position. On the rotor side, again, we have laminations pressed together. We may have some sort of sensor magnet or sensors inserted onto the rotor. We have permanent magnets that are pressed into the rotor. So we can see those here, these little slots. And these can either be pre-magnetized, where they're magnets and we push them in, or they're not magnets and we pulse flux at it. So if we look at all these things, what are things that can be done that are incorrect in the manufacturing process? Well, one, we can have magnet failures. We can have magnets inserted backwards. We can have magnets with the wrong polarity. We can have magnets that were not magnetized enough. We can have magnets that are magnetized too strong. Upon insertion, we could have magnets that are broken. So there's a lot of different things that could go on with the magnets as they're being inserted. And that's probably going to be the main thing we look at with the back EMF test. We have sensor functionality, those position sensors, whether it's a resolver or a simpler sensor. Those can have offsets. Those can be broken upon installation. The windings could be incorrect. We could have a sensor misalignment. We could have incorrect wiring harnesses. And these are all, or largely, things that could be covered with a rotational test or a rotational back EMF test. So that's really how we get to the back EMF, is that we can tell if a magnet's failed. We can, through a rotational test, we can tell if the sensor's functioning correctly. We can tell if our wiring is correct. We can look at sensor misalignments. So there's quite a bit going on. All right, so what does a back EMF test look like? Getting into kind of the nuts and bolts. Well, it's pretty simple, and I have a very simple animation to show it. So typically, we're going to test just the rotor. We could test the rotor and stator as a combination, but that does not necessarily tell us if the failure was in the stator or the rotor. So I'm going to speak today to kind of a generic setting where it could be either. But for the back EMF test, if you're testing the magnets, I really like to do the rotor by itself with a stator with a known number of turns, and then those voltages open circuited so we can measure that voltage. So we're going to have, let's call it a golden stator with a fixed number of turns. We're going to have a tester that spins the machine. So it's going to spin that rotor with the magnets on it. If we're testing position sensors, we're going to have excitation for that. And then we're going to need data acquisition equipment and some software to make logic. And basically what we end up with is we have a machine that spins a rotor past stator windings, and we're going to generate a voltage just like in my animation here. We're basically creating a generator. I don't think anybody's surprised by that. But so this is the basics of our test. What that physically looks like, if we actually go into the test stand, we're going to have the assembly line, and please forgive my animations. We're going to have an inverter and a drive motor in that test stand. And then we're going to have our device under test, a rotor under test. That rotor under test is going to get placed into this drive motor. This drive motor is then going to be inserted into our test stator, and we're going to spin up this rotor. The magnets, my blue and red squares, are going to excite those stator windings because we have a known number of windings, and we're going to create those three-phase voltages. Those three-phase voltages are going to be read into something like HBM's eDrive system. If we have position sensors we're testing, we can potentially bring those into the data acquisition system as well. We're going to acquire data for a period of time. We're going to stream that out to a PC, or in some instances, we can actually do that all in hardware. And then we're going to give a pass-fail command to the assembly line so it can decide where to put that rotor. Does it go in the junk bin? Does it go onto a further part of the assembly line? So this is the basics. We insert a rotor, a test rotor, into a stator. We spin it up. We take some measurements. We do some pass-fail analysis. So let's look at a back EMF test example. All right, now, per normal, not too many people give me access to their data. So I had to take a power drill, bought a DeWalt drill, took it apart, and I'm going to run a back EMF test with this power drill because the test is pretty simple at the end of the day. It's really the analytics and the data acquisition that's the hard part. So we have our stator. This is our golden stator, which is actually just the production stator. We have the part under test, where we have the permanent magnet rotor, and the magnets are buried, but trust me, they're there. And then we have some position sensor circuitry, because I think the position sensor is kind of a two birds with one stone test with the back EMF. And we're going to have this rotor inserted into the stator. We're going to spin it up, and we're going to make some measurements. So it's a permanent magnet rotor. It's a 4-pole rotor. So we have 4 pre-magnetized bar magnets, which are inserted into the machine. We have a 3-phase test stator. The rotor is inserted. The rotor is spun at a fixed speed. So for this first test, we're going to show fixed speed. A little later, we'll show something a little more interesting. And then the voltage and precision measurements are taken. So nothing fancy. Rotor gets put in a stator, rotor gets spun, measurements get taken, decisions get made. So what's kind of our data acquisition and post-processing decision-making flow? So for a given rotor, we're going to have a min and max tolerance for our KE, for our machine constant. We're going to have an angle offset tolerance. This is for our position sensor. And then we're going to have a known frequency and voltage. So we can look at these 4 different things and decide, okay, is something wrong? Is something right? We're going to run the test. We're going to acquire the data. We're going to look at the signal levels and just say, hey, are our signal levels okay? Did this test actually run? It's kind of the first validation state. We're going to determine the electrical frequency. So we're going to say, okay, is this motor even spinning at the speed we expect? If we get that speed, we're going to take our voltage, we're going to take our frequency, and we're going to decide what the machine constant is. We're going to calculate the angle and position between the 3 phases and then the position sensors. We're going to look at the polarity of the signals, and we're going to do a pass-fail. So we're just kind of incrementally checking, are my signals okay? Is my speed okay? Is my calculated values okay? Are my positions okay? Were these things installed backwards? Pass-fail. And I don't think anybody was surprised. We're going to have those 3 phases coming into our instrument. We're going to have those position sensors coming into our instrument. The test rig is going to place the rotor in the stator. The test rig is going to spin the rotor to speed. We're going to take 0.1 seconds of measurement. We don't need a lot of measurement, so we can have a really high throughput. We're going to pass the data through the analysis. We're going to give a pass-fail, and then we're going to archive that failure data. Archiving the failure data is a really cool thing that HBK can offer, because every time you run a test, you can store the past data, you can store the fail data, and then later, if you're having quality issues, you can always have that data to reference back to see if your suppliers are having issues, to see what's going on in your supply chain, to see what's going on in your tests. So nothing fancy. Again, rotor goes in stator, we spin it up for a very short period of time, we run some analytics, we store some data, and we actually display that on a screen, and then we can give you a pass and or fail. So let's look at some examples from this test data. Okay, so this is data that we took from one of those 0.1 second test runs. And there's a lot going on here, so I'm just going to walk through it kind of slowly, and I apologize for the poor resolution. I probably should have formatted this better. But what we have are these 3 sinusoidal traces that are purple, blue, and red. These are our 3 phase voltages coming out of that stator. So we've spun our rotor to speed, and we're measuring the generated voltage. This is our back EMF. This square wave here, this black square wave, is actually our position sensor. So this given motor has a Hall effect sensor, so it's a very basic position sensor. But what we're looking at is the falling edge. So what we're going to determine is, okay, I'm going to look at the peak voltage, so my KE, and my frequency, generated in this instance by my position sensor. I'm going to say, okay, I have my peak voltage, and I'm going to divide that by my no-load speed. So we're going to get our RPM, and we're going to say, okay, here's my here's my KEs. My 3 phases of KE are all in the passing range, and they're close enough together that we're going to get a nice average, and we're going to pass that KE value. So our voltage level is what we expect. Our speed is what we expect. We're going to pass that KE. Now we're going to look at position, and we look at that falling edge of my position sensor, highlighted by black here. And again, I apologize, this was a little busy. I probably should have been more clever with my display. And we're going to look at what is the angular displacement between my position sensor and the rising edge of my 3 phases of back EMF. Anybody who's done any sort of DQ control knows that you need to have your position sensor correctly aligned to your voltage, your back EMF. So we're going to look at the 3 phases. We're going to decide if our position sensor is correctly aligned to those 3 phases of back EMF. And if it is, then we pass. And if we're not within an angular tolerance of our back EMF, then it's a fail. So we calculate our value, we look at the plus or minus, and we decide if we pass or fail. So the position sensor alignment, we look at the rising or falling edges, and we calculate the edge to each phase 0 to decide if it's a pass or fail. So we're looking at that voltage, and we're looking at that angle. We're comparing to known tolerances, and we're giving a pass on angle, a pass on back EMF, and then a pass on polarity, and a total pass, and then we're going to give that information back to the automation system. So this is a passing test. What might be a little more interesting is some failed scenarios. And maybe I should actually start with the failed scenarios. They're probably more interesting. So here we can look at our 3 phases of back EMF, and we can say, okay, these have the peaks we like, we're going at the correct speed, but that position sensor is dead in the water. So this is an example of our position sensor. The wiring harness was incorrect, maybe the excitation wasn't there, but the sensor wasn't getting excited. So we pass our KE, but we fail our angle because our position sensor is not working. So this is an example of a overall fail. In this next example, my speed was correct. My position sensors are correct. So we get a pass on position, we get a pass on polarity. But if we look at our voltage, this peak is incorrect. So, okay, this might indicate that my magnets were not magnetized correctly. So I get a fail on my KE because my voltage peak was not high enough. Now I'm going to take a moment here to kind of go back and mention what I had talked about earlier, that I don't necessarily like peak voltage as the metric for KE. Because with these more complicated rotor geometries, as we get more magnets, as we get different angles and shapes of magnets, peak voltage doesn't really give us the whole story. If I look at my back EMF here, where I have this kind of nice triangular shape, we could see a back EMF where we maybe have a V shape, or we have kind of a crown shape. And if one of my magnets, let's say I have 3 magnets, if one of my 3 magnets is weaker, my crown shape might not be correct. Fortunately, with the HBK back EMF tests, we can actually start to look at things like harmonics. So we can look at the harmonic content of the back EMF waveform. We can look at the shape of the back EMF waveform. We can look at the area under the curve of the back EMF waveform, in addition to that peak voltage, and use multiple metrics to decide if we're passing or failing. So this is actually going to raise our throughput because we're just going to have more metrics rather than just peak voltage. Because back EMF, as I mentioned, is not as simple as just a peak voltage per speed. Given these permanent magnet rotors, we need to start looking at more metrics other than just peak voltage. And I think harmonics, area under the curve, wave shape are really good starting points. And I'm going to propose another potential method in a moment that actually does all of this in one test that could also be included. But again, these are some examples of failed sensor, failed voltage. And when we have these failures, we can store all of this data, send it to the cloud, and then these data can be used for R&D or quality control. Now, KE is kind of interesting because it is ratiometric. So if we go at a slower speed, we can actually pass a KE because our voltage per speed is a ratio. So this is something to keep in mind. And I typically like to operate at a fixed speed if you're doing a KE, just because to keep things more constant. But our position sensors will pass, our KE will pass, and it can be a flexible test. But in practice, this isn't perfect. So I'm kind of setting this up to show one of the methods that we like to use for these back EMF tests. So just keep in mind that, again, peak is not always the best metric. It is a metric, it's a useful metric, but there's more things we can do. So let's look at an advanced back EMF test, and I'm not going to go through all the details of area under the curve or harmonics. We're going to look at the magnetic flux method, which actually does not require a constant speed. So my test procedure is going to be basically the same, except now instead of running the back EMF equation or the KE equation, I'm going to run a flux equation. So this flux equation is really cool because it does not require a fixed speed. It doesn't even require a constant speed because we're actually calculating the magnetic flux of the magnets. Position calculations can still be done. And it's a possible method if you cannot use a fixed speed rig. It's a possible method if you have a lower throughput and you just want to spin things by hand. But I actually like it even for fixed speed tests because it's another data point. We can take our KE values, we can take our flux values, and we can start to have more points to check for failure. So let's look at this flux method, and I'm not going to walk through the math of it. We can take that offline if you're interested in the math. Basically, we run some space vector calculations and then do some mathematics to get to flux. So here is my constant speed test. This is actually the exact same test that I ran in the previous section, 3000 RPM, 4-pole machine. And we can see, all right, now I'm measuring line to line instead of line to neutral, and I get this little V shape, but I get my my 3-phase voltages, my position sensor still working, and here's that calculated flux value. And you can see we have a little bit of time for that thing to ramp up. It comes to a steady state value, and then the calculation kind of ramps down. It's an integrator windup. But we get a flux value of 2.23 millivolt seconds. Let's look at the same machine, except now we start at 0 speed. we spin the machine up, and then we spin the machine down. So we're starting at 0, we're spinning rather than a fixed speed. We run that flux calculation, our position sensor still works, our position test still works, and we can see we still have that ramp up period of the math. This is my flux calculation, but we still get that steady state, and then as we ramp down, we kick off. So as we're ramping up in speed, because this whole test is a speed ramp, we can see our position sensor like getting tighter and tighter, and then wider and wider. We get a fixed value of 2.26. We're within a noise range. So during this increasing speed test, we get the same value as the constant speed test. This flux calculation is really powerful if we don't have a great automation system, if we're doing things by hand, or if we want another data point. Now let's take that a step further. Let's look at a back EMF test just spinning the rotor by hand. So this is no constant speed. There's not even an idea of having a constant speed. Well, if we look at one of these individual segments, we can see that we're constantly speeding up, constantly slowing down. My position test still works, and I still get a valid flux value. So my flux is 2.27. We're still within a really reasonable range. And if I look at a variety of hand twists, so this was me running the test several times, just twisting that rotor by hand, the position test works. I get a constant value of flux for all of these tests, even the really crappy one I did. I had a weak wrist on that one. We can see that constant speed 2.23, increasing speed 2.26, strong hand twist 2.27, weak hand twist 2.25. This test is, it doesn't care about speed. This test doesn't care about my peak voltage. It doesn't care about the area under the curve. It just calculates the magnetic flux. This is a really good data point for did my whole rotor pass? And then we can use other tests to determine how things failed. But it's a really powerful test. It's a very good validation, and it just looks at the magnetic qualities. So it's a really, really powerful back EMF test that can be run under any scenario. We don't have to worry about those peak voltages. We don't have to worry about the different shapes. This accounts for all of that in the test. So, in conclusion, what can HBK do in this arena? Well, we have a system we call our eDrive. We can record a lot of data for quality control. We can edit all of the equations. We can incorporate things like the back EMF test, the harmonic tests. We can change variables and tolerances as needed. And we have a software where you can visualize, do automation, give feedback, or you can take our software out of the loop and just operate in hardware. So we offer sensors, software, and data acquisition that has some really advanced features. As these permanent magnet rotors become more complex, we can offer you a wide set of features to do this type of testing. We offer open and editable equations for your KE or for your flux or for your harmonics, where you can actually go through the equations, you can understand exactly how everything works, you can edit them, we can do position equations. All of our equations are viewable, all of them are editable. We can run them in the post process or in the real time. You can tune your test stand. You can do one test, edit the variables to prep for new products. You can really own the control of your test stand. For those who want to be more automated and maybe not have as much control, we can offer custom GUIs and workflows where you can have an operator log in. You can scan a label with a barcode. We'll set up what the tolerances are for that magnet or for that rotor. You can connect the individual phases to the motor. So we can actually give it so an operator knows where to make connections if it's more of a manual process. We can give you the measurements not okay, but you should repeat it. The measurement fails or the measurement passes. These are things we can offer as a custom setup for your needs if you want to have a GUI. So in conclusion, back EMF tests are easy to evaluate the magnetics and position sensors of your production motors. Advanced equations allow for flexible test stands, and they also take out the uncertainty as we get to more advanced motors, more complicated back EMF profiles. Data storage allows for quality control and traceability. You can always send data to the cloud. And the HBM eDrive has transparent and editable equations. So with that, I'm going to close out. If you want to connect with me, please scan this with your phone for LinkedIn. If you want to learn more about HBK's products, please scan here, and it will take you to our webpage. Thank you. Bye.